Hello, everybody. This is Bert Dixon here presenting on graphs of ellipses. This is corresponding to section 10.2 in your CPM pre-calculus book. So this whole chapter is on what we call conic sections, and they're called conic sections because they are shapes that you get by taking cross sections of a double cone. And so I'll show that here in this YouTube video. We see that we get a parabola. So where the plane touches the cone is in the shape of a parabola. Okay, and so we'll see what different shapes we get when that plane is tilted. So that's the view of the parabola. Now we see if you have if you slice the cone with a tilted plane, it intersects the cone in the shape of an ellipse. And if it's horizontal, it's in the shape of a circle. If the plane intersects both the upper cone and the lower cone, then it creates what we call a hyperbola. So we'll learn that in the next section, 10.3, I believe. And it's possible to just get a single point. So we get circles, parabolas, ellipses, hyperbolas. You can even get a line if you just let the plane touch along both of the cones, then you could get a line as a conic section as well. Okay, so back to our notes. We're focusing on ellipses today. And so an ellipse is a figure that has two focal points. Plural of focus is foci or foci. So F-O-C-I is the plural of focus. So we have one focus or we have two foci or foci. You can pronounce it either way. And so the definition of an ellipse is that it's a set of all points such that the sum of these focal radii are the same. And so if we call this distance 1 and distance 2, distance 1 plus distance 2 remains constant. So anywhere that I go on this ellipse, distance 1 plus distance 2 is always equal to the same number. And so that is the definition of an ellipse. And then we see in the diagram down here that the distance from the center to the focus, we call that C. We have a major semi-axis, which is the distance from here to here. That's going to be A or B. Doesn't really matter which one's A and which one's B. And all that you need to know is the one that's under the x squared is the distance, is the length of the semi-axis in the x direction. Whatever's under y tells you how far we're going vertically. So horizontal is what's under x, vertical is what's under y. And then the relationship between A, B, and C, if we call this A and this is B, then if A is bigger than B, then C squared is A squared minus B squared. If B is bigger than A, then C squared equals B squared minus A squared. So again, remember, it doesn't really matter which one we call A and which one we call B, as long as when we're finding C squared, we do the larger one minus the smaller one. So we're always going to get a positive number for C squared. And back to this definition up here, I've got a quick demonstration to show how the ellipse is created. So I'll go ahead and show you that video. So what I have here is a piece of string with two loops in the end and a couple of tacks. So let's imagine we wanted to draw an ellipse that has focal points here and here. And so what I'm going to do is take one end of the string and fasten it to that point, and the other and fasten it there. And so that way when I pull the string tight, we get a constant length. So the string is not going to change length. And so by pulling those tight, that maintains a constant sum of those lengths. So the two pieces of string are always going to add up to the same amount. And so when I pull it tight, that constrains where my pen is able to draw. And so what that's going to do is create an ellipse. So if I go to the other side, we'll see the same thing. Keeping those strings tight. And that is an ellipse. And so if the center point is right about here, then that distance is C. And the longer axis is A, or B, doesn't really matter. And then this one would be B. And any point that I pick on the ellipse, we imagine where the string was tight, that's there from focus to focus. From that point, this distance, D1, and this distance, D2, will always add up to the same amount. So D1 plus D2 is equal to some fixed constant. Okay, another quantity that we need to be able to calculate with an ellipse is the eccentricity. So eccentricity tells you how circular the ellipse is. So if it's a perfect circle, the eccentricity is 0. If the ellipse is elongated, then the eccentricity is going to be something closer to 1. So this might be an eccentricity of about maybe 0.95 or something like that, because it's a long and skinny ellipse. So elongated ellipses have an eccentricity close to 1, and very circular ellipses have an eccentricity closer to 0. Okay, so we'll do a couple examples of graphs. So in this first example, go ahead and take a moment and copy this down. Okay, so this one is centered at the origin, because it's just x squared plus x squared over a squared plus y squared over b squared equals 1. So that's centered at the origin. And so this is 5 squared. So since that's under x, that's going to tell us how far to go from the center in the x direction. So we count from the center 1, 2, 3, 4, 5 to the left or to the right, and 1, 2, 3, 4, 5 to the left. So 5 to the right, 5 to the left. And then whatever's under y tells us how to go vertically. So 9 is 3 squared. So we're going to go 1, 2, 3 up and 1, 2, 3 down. Okay, and so now we're ready to draw our ellipse that goes through those 4 vertices. Okay, so you can freehand that to go through those 4 points. So there's our ellipse. And so now we just need to find the foci and the eccentricity. And so c squared is equal to the difference between these values, a squared and b squared. So we always do the bigger one minus the smaller one. So 25 minus 9. So c squared is 34. And so c is the square root of 34, which is just a little bit smaller than 6, because the square root of 6 is, the square root of 36 is 6, and so the square root of 34 is 5.83. So we'll say about 5.8, and so the foci are always on the longer of the two axes, so we call that the major axis. So we count 1, 2, 3, 4, oh, sorry, this is 16. Let's start that over again. C squared is equal to 16, so C equals 4. And so we're going to count from the center, 1, 2, 3, 4. The foci are always on the longer of the two axes. So this is C equals 4, tells us that that focal point is 4 units from the center along the major axis. 1, 2, 3, 4. There's our other focal point. So our focal points are at negative 4, 0. And positive 4, 0. So we could call one of them focal 1 and focal 2. Okay, and so now we have our two focal points, or foci, and then we're ready to calculate the eccentricity. Eccentricity is C over the larger of these two values, so a 5 or 3, in this case it's 5. So C over 5, C we said is 4, so our eccentricity is 4/5. So that was an example with the center at the origin 0, 0. Now if we translate our ellipse so it has a center at HK, then this is the equation that we get. So it's the same as the equation we used in the previous example, except it has, in place of x, it has x minus h, and in place of y, it has y minus k. This is the same format we've seen for translating functions throughout, for any graph. Whenever you replace x with x minus h and y with y minus k, it's going to shift the graph h units left or right and k units up and down. Okay, so for example, h is 3, and k, since this says y plus 1 and the standard form has y minus k, then k must be negative 1, because y minus negative 1 becomes y plus 1. And so k would have to be negative 1. So our center for this ellipse is at 3, negative 1. And so now we're ready to graph this. So 3, negative 1 is here. There's our center. This is 4 squared, and that's under x, so that tells us how far to go in the x direction. So we'll go 1, 2, 3, 4, 1, 2, 3, 4 for x. Under y is 6 squared, so that tells us we're going to go 1, 2, 3, 4, 5, 6 in the y direction. Create a little more space here. So 1, 2, 3, 4, 5, 6. Okay. And so our ellipse then is going to go through those 4 vertices. Right there, up here, and down here. Okay? And since our major axis is vertical this time, we know our focal points are going to be on the vertical axis instead of the horizontal axis. And so we get c squared is equal to, remember we always do the bigger one, the bigger denominator minus the smaller denominator. And so that is c squared equals 20. So c is the square root of 20, which is about 4.5. And so if we go up 1, 2, 3, 4.5, we have a focal point here, F1, and that should be from our center, 1, 2, 3, 4, yeah, 4.5, and 1, 2, 3, 4.5, about right there. Okay, now when we write the coordinates, I'm not going to say it's at 4.5, I'm going to say it's at a y value of, or sorry, the x value is 3, because remember our origin is over here. This is 0, 0, and so this point is at x equals 3, and the y value is -1 plus the square root of 20. Square root of 20 is 2 root 5. So we could say -1 plus 2 root 5. And then this point down here, focal point 2, is 3, comma, -1 minus 2 root 5. So those are the coordinates for our two focal points. And then our eccentricity is c over the larger of the two values, which is 6 between a and b. And so root 20 over 6 is about 0.75. Now I'd like you to go ahead and try example C on your own. So pause your video, try example C, find the focal points and the eccentricity, and then press play to check your solution. Our center for this ellipse is at -2, +5. So our center is here. We're going to go 7 units in the y direction, because this is 7 squared, 2 units in the x direction. And so I'm going to need a lot more space here. So I'm going to move this down. And so from this center point, I'm going to go up 7. 1, 2, 3, 4, 5, 6, 7, and down 7. 1, 2, 3, 4, 5, 6, 7. And then in the x direction, we're going to go 2 to the right and 2 to the left. And so our ellipse then is going to look like that. Okay, and again, our focal points are always on the longer axis, so we know they're going to be on the vertical axis. And so c squared is equal to 49 minus 4, which is 45. So c is the square root of 45, which is 3 root 5. And that is about 6.7. And so if we go up 6.7, that's going to put us right there near the edge. And then down here, because we know that the full distance is 7, so 6.7 is very close to the full length. And so we see when the value of C and B in this case are very close to each other, C is about 6.7 and B is 7. That makes our eccentricity very close to 1. So remember I said a circle has an eccentricity of 0, and the largest eccentricity you can ever get is 1. And so an eccentricity getting close to 1 makes it very elongated, whereas an eccentricity close to 0 makes it circular, or near circular if you're close to 0. Okay, and so our our eccentricity for this problem is 3 root 5 over 7, and that is pretty close to 1. That's about 0.96. So very close to 1, that makes it elongated, whereas a E value close to 0 is nearly circular. Okay, and now so our focal points have coordinates of -2, and then our y value started at 5, and then we add 3 root 5. So it's -2 comma 5 plus 3 root 5. This one down here is going to be -2 comma 5 minus 3 root 5. Okay, so we have our two focal points, we have our eccentricity, and we have the graph of our ellipse. That's it for today's lesson. Have a great day, everybody.